G'day, I'm James, and here's a very famous math problem that appears in absolutely every textbook on this planet, especially on the chapter on quadratics. It often appears in the chapter on calculus as well, and it's this problem. A farmer has 40 meters of fencing and wants to make a rectangular pen of maximal area, biggest area possible. What should the dimensions of that rectangle be? Okay, grand fine. Okay, first of all, I doubt this is really a practical problem. I don't think anyone actually thinks and works that way. So it really is just an exercise in practicing the tools of mathematics. So if this is in a quadratics chapter, you're meant to be practicing the tools of quadratics. In a calculus chapter, the tools of calculus. That's okay, that's all good. But I'm not going to do any of that. I'm going to see if I can just step back from this problem and deduce what the answer should be. All right, so let's think about this. So we're making rectangles, perimeter 40, and we want to get the rectangle of maximal area. The rectangle of maximal area. That makes me think there's going to be one answer. In fact, it really matches my intuition, because I doubt it's going to happen that you can make one rectangle over here of maximal area and make a completely different rectangle over there of the same biggest area and have two different answers to this problem. That just doesn't feel right to me. I really do think there's going to be one answer here. Okay, in which case, what would the one answer likely be? What is the one special rectangle you could make out of all possible rectangles of perimeter 40? Well, you have to say to yourself, well, there's only one special rectangle in mind. It would be the symmetrical rectangle, the square. The most symmetrical rectangle seems to be the special one amongst all rectangles. So I'm going to guess that is the answer to the problem. I bet the answer is going to be the most symmetrical rectangle you can make. That seems like the only special rectangle amongst them all. I bet it's the 10 by 10 square of area 100. Okay, so that's my intuition right there. So to actually answer the question, let me actually give an answer based on my intuition. Now I don't know if that's actually true or not, so I'm going to do this. Okay, let's start with what I think is the answer and ask how far off could I be from my guess? So this side is probably shorter than 10, so it's probably 10 minus x. And this side is probably longer than 10, it's going to be 10 plus x, 10 minus x, 10 plus x. So actually every rectangle could be thought of as this way, as deviating from a square. Shorter than 10 and longer than 10, and that is still perimeter 40. Great. So I'm actually starting my answer here, my thought process here, for what I suspect is the answer, and seeing if that helps me out. In fact, let's see if it helps me out, because I want to know the area. What's the area of this general rectangle? It's going to be length times breadth. It's going to be 10 minus x times 10 plus x. Expand that out, so I get 100. Cross terms go away, minus x squared. The area is always 100 take away something. Now it's clear I get maximal area when I take away nothing. Maximal when x equals 0. That is, I have no deviation from my square solution, no deviation from the symmetry. Whoa! So maximum for a 10 by 10 square. There it is. I use symmetry to my advantage to make this problem fall into place very, very swiftly. Whoa! Okay, let me summarize what we've just learned about rectangles. We've got a rectangle with two unknown side lengths. I'll call them x and y. And we're given something about that rectangle, namely the perimeter, 2 x's and 2 y's, has a particular value, 40 meters. That is, we're given two unknowns whose sum has a fixed value, dividing by 2, x plus y is 20. We have the goal of actually maximizing the area. Please maximize the area, which would be length times width. Please maximize the product of those two numbers. Then we know the answer is actually symmetry. We just saw the answer is symmetry when we have a perfect square. The answer is symmetry when we have x equals y. So there's a nice way to summarize what we've just learnt. Grand and good. Now, that classic problem about 40 meters of fencing always comes with a part B. There's always a follow-on problem, and it's this one. Imagine that farmer has a big barn on her property. So here's one side of a barn wall. And now she's going to use her 40 meters of fencing to actually make a rectangular pen with 3 sides of the rectangular pen being the fencing and the 4th side being the wall of the barn. So now all the fencing is just being used for 3 sides, not all 4 sides. Okay, what are the dimensions of that rectangle that gives biggest possible area? All right, I'm going to answer that question. I'm going to use symmetry to my advantage. In fact, I can see two ways to use symmetry to my advantage. Here's the first way. Geometric symmetry, I'll call it. Geometric symmetry. What I'm going to do is actually make this picture more symmetrical. And how am I going to do that? Sneaky. I'm going to be sneaky. I can imagine this barn wall is actually a mirror. It's a mirror. You can see the reflection of all that in the mirror. In fact, what you would see as reflection would be what looks like another copy of that rectangular pen over there that uses another 40 meters of fencing. So when you look at this in the mirror, it looks like you're now making a four-sided rectangular pen just like before, but using 80 meters of fencing. Now, we want to maximize this area right here. But there's actually another copy of that same area there. This is double the area we want to maximize. So if I get the biggest area possible here for what I see as the four-sided pen, that is half that biggest area there, that corresponds to the biggest area of just half that pen of what I'm seeing, the actual physical pen. All right, so maximizing this whole area here does the same job for me as maximizing that area just there. Great, great, and good. All right, so where did I get the maximal area for four-sided pen using 80 meters of fencing? When I have symmetry, when I have a perfect square, I'll use 20 meters there, 20 meters there, 20 meters there, and 20 meters on top. Great, that gives me the biggest possible area for what I'm seeing in the reflection. But of course, what I'm doing physically then, yes, I will use 20 meters across there, but I'll use half of 20 there, 10 meters there, and 10 meters there. Bingo, 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 that does it. The rectangle, or biggest possible area here, is the 10 by 20 rectangle, and that is indeed perimeter 40. Good, we got it. Geometric symmetry. But let me do it again now by using another type of symmetry. Let me just redraw this picture. Let's pretend we didn't see the answer there and do it again. So I have a barn wall. I have a rectangular pen with 40 meters of fencing there. Now I'll do what I'm going to call algebraic symmetry. Algebraic symmetry. I'm going to use all the algebra over here. All right, so I've got two unknowns. I want the width of the rectangle and the length of the rectangle and the width again over yonder. All right, we are given that I'm using 40 meters of fencing to make this picture. 2x's plus y equals 40. And now I'm already nervous because it doesn't look like I have symmetry. Our goal is to maximize the area. Maximize area is going to be x times y. Okay, that looks good, but I don't have symmetry there. Okay, so it looks like things aren't good right now. Aren't good. But I could argue this. Well, my unknowns are really 2x and y. Let's think of those as the unknowns. And instead of maximizing 1xy's, I could also maximize double xy. If I make double the product as big as it can be, then halving it means the original product was as big as it can be, and vice versa. If I make the product as big as it can be, if I double everything, then double the product as big as it can be. So actually, these are equivalent problems. And the reason I like this version is I can think of this as 2x, my first unknown, times y, my second unknown. Given two unknowns of a fixed sum, got it. Want to maximize that product, got it. Then the answer is when we have the two unknowns equal each other, when we have symmetry. So we need symmetry. I need this unknown 2x to equal that unknown y. Whoa, I used it, I got it. All right, so this is equal to that, and they add up to 40. So if this is equal to, if these things are equal to 40, that must be 20. That must be 20. That tells me answer is, I'm being a little bit sloppy with my board technique. 2x is 20, so x is 10, and y is 20. Y is 20. 10, 20, 10. The answer we had before. There's algebraic symmetry. There's using this result right there. Whoa! Let's do another one. I'll be right back. I've got to clean the board. Okay, now our farmer's getting crazy. With the 40 meters of fencing, she wants to make this diagram. A big rectangular pen divided into 15 smaller pens. All with that 40 meters. And she wants the total area here to be as big as it could possibly be. So what should the dimensions be to get a rectangle of biggest possible area? All right, so let's see. So let's give two unknowns. So let's call that dimension there x and this dimension here y. What are we given? So 40 meters of fencing and making all of that. So I've got 1, 2, 3, 4, 5, 6 x's, 6 lengths of x, plus 1, 2, 3, 4 lengths of y is all my 40 meters of fencing. 6x plus 4y is 40. What's our goal? Our goal is to maximize the total area, which is x times y. We've got like a mismatches here going on. Oh, well, rather than maximizing just one copy of the product, we could equivalently maximize 24 xy's. Make that as big as it can be, then divided by 24 means that's as big as it can be. Great and good. And why do I like 24? Because I was quickly think of this as 6x and 4y multiplied together. They're my unknowns, and I want to maximize that product. Two unknowns of a particular sum, and I want to maximize that product. I know the answer is when we have symmetry. One unknown equals the other unknown. 6x equals 4y. So this unknown plus that unknown are equal and up to 40. This better be 20. This better be 20. So 6x is 20. So x is 20 over 6, 10 over 3, 3 1/3. This must be 3 1/3 meters. And 4y is 20, y is 5 meters. That does it. The power of algebraic and geometric symmetry. This is wonderful. Okay, let me take a different approach to rectangles and squares. So let me draw a general rectangle. I'll call it side lengths x and y. Our theme so far has been having the same perimeter, always 40 meters. So let me ask this. Let me associate with this rectangle a square of the same perimeter. What would its side length have to be? Okay, I'll use W for what there. Okay, well, I can ask that question. I mean, the algebra here is straightforward. I want the perimeter of the square to be the same as the perimeter of that rectangle. Thus, I want 4 w's to be matching 2 x's and 2 y's. Divide everything by 4. W must be x plus y over 2, the average of those two side lengths. In fact, the fancy name for this is the arithmetic mean of x and y, arithmetic mean, which people usually denote with a capital A. So if you want a square of the same perimeter as a given rectangle, then make that square have side length the arithmetic mean of the two original sides. Great! Now, of course, if I've got a square of the same perimeter, it seems very natural now to ask, well, what about a square of the same area? Could I get a square of the same area? Well, the answer is yes. I don't know what it's going to be right now. I'll just use W for what. But algebra will tell me that if I want the same area, I want W squared, the area of the square, to be the area of the rectangle, x times y. So W have to be the square root of x times y, the square root of the product. And that also has a name. It's called the geometric mean. The geometric mean of the two numbers x and y, usually denoted with a capital G. So if you want a square of the same area as the original rectangle, make its side length the geometric mean of the two original numbers. Grand and good. Now it looks like I've drawn my picture so that these two squares are actually the same size. Is that likely to be the case? In fact, I could argue that maybe this picture here is a little bit bigger than that one there. Is this picture always greater than that picture? Is this square always bigger than that square? Okay, is there any relationship between the sizes of those two squares? And the answer is yes. This square is always going to be bigger than that square, despite my picture. But let me show you why. The key is to actually draw 4 copies of the original rectangle and do it like this. Here's my little rectangle, so I'll do x by y. Then I'll do a little extra x and then come down y, x and y. Little extra x and come across y, x and y, and then over by x and up by y, x and y. Arrange those 4 rectangles to make a square. Always squares, I'm focusing on squares. It looks like we've got some space in the middle. So let's be very clear. How big is that space? This is a full length y across there, and that's a length x. I guess I'm assuming y is bigger than x in my picture, because that would be the length y minus x. So that is definitely y minus x across. So if x is different from y, if x is different from y, because I'm kind of assuming y is bigger than x, then I've definitely got some space right there. Fine. Now let's play with this picture. I've got a great big square. I've got a great big square of area x plus y squared. Clearly this whole area here is bigger than the area of just the 4 rectangles combined, because I've got that space in the middle. So it's definitely bigger than the areas of each rectangle's 4 copies of. It's bigger than 4xy. Take square roots, I can now see that x plus y is bigger than 2 root xy. Divide by 2, I can now see the arithmetic mean is bigger than the geometric mean. If the two numbers are different, if it's definitely a rectangle with side y longer than side x, then this square of side length a is definitely bigger than this square of side length g. Now I guess I'd better check what happens if x equals y. If I've got equality here, what's going on? Well, if x equals y, that means, oh, that's 0 length there, I've got no space. If x equals y, this is actually a square. What I'm really doing then is actually stacking 4 squares together with no space right at the middle. In which case, I've got equality here. There's no space in the middle. And in which case, I've got equality here. In which case, I've got that the arithmetic mean equals the geometric mean. Which actually you check the formulas. If x equals y here, you'll get x. If x equals y here, you'll get x. We do have equality. So now we've got it. The arithmetic mean is always greater than or equal to the geometric mean with equality only if we've got squares, x equals y. So that's a very, very famous inequality in mathematics. And let me just write up formally right here. So we have it on the board, and then we'll play with it. Let me clean the board though, back in a moment. Okay, so here it is, the arithmetic geometric mean inequality. For two positive numbers, x and y, their arithmetic mean is always greater than or equal to their geometric mean. And we have equality only if x equals y. That is, we have symmetry. Always symmetry. Love it. Let me just point out how my brain works. I actually, most people present this, but I actually like to double everything, multiply this by 2, and say, that is, we have that x plus y is greater than or equal to square root of xy plus another square root of xy. My brain likes this version of the inequality because it's what it's saying in my head, that the sum of two different numbers is always greater than or equal to the sum of two of the same number, that same number being the geometric mean. And we have equality, of course, only when x equals y, symmetry. So for some reason my brain likes that. In fact, it's kind of helped what we've been doing. We've been having sums like this of a fixed value. So note this. If x plus y equals a fixed value, I'll call it s, then we have that s, which is x plus y, is greater than 2 root xy. Divide both sides by 2. That tells me s over 2 is greater than or equal to the square root of xy. Let me square both sides. It tells me that xy, the product, is always less than this thing. That thing is just a number. So if you've got two unknowns but with a fixed sum, then that product is always bounded by some upper bound, some whatever that number is. And we know we'll get that biggest product possible when we have equality here. That is when we have symmetry. Two numbers with a fixed sum have biggest product when we have symmetry. Whoa! So there's a consequence of the arithmetic geometric mean inequality. So let me just write that up as a formal consequence. So I'll do this in orange just for fun. So here's a consequence. If x plus y has a fixed value, then the product is maximal when we have symmetry, when x equals y. So there is a formal consequence of the geometric mean inequality for the ideas we've been doing all along in this video so far. In fact, let me solve one of the previous problems using this result right here. But I need more room on the board. Okay, let me do it. Back in a moment. Okay, so back to our farm with 40 meters of fencing, building a rectangular pen against a bound wall. I'll call the dimensions x and y, but we're told that 2x plus y adds up to 40 meters. So two unknowns, 2x plus y, adding up to a fixed sum. We want to maximize x times y, the area. Well, we might as well maximize double that, 2x times y, the product of our two unknowns. And we know the answer is going to be when we have symmetry, when our unknowns are equal to each other, 2x equals y. So this equals that, and they add up to 40. That must be 20. That must be 20, in which case x is 10, y is 20, the answer we had before, just from the arithmetic geometric mean inequality. Whoa! Here's the arithmetic geometric mean inequality for two unknowns, x and y. And if you like, I can think of this as a two-dimensional statement. Here's the amazing thing. This inequality actually generalizes to higher dimensions, to more than two unknowns. And that's what I'll talk about right now. But before I do, I just have to mention, I think I've got myself in a little bit of a pickle, because right now I'm using the symbols X and Y. That is the end of the alphabet. If I want more unknowns, I think I'm going to run out of letters. So let me start by rewriting this in terms of letters at the beginning of the alphabet. Okay, give myself enough letter space here. Let me write this version. The sum of two distinct quantities is always greater than or equal to the sum of two of the same quantity, twice of the geometric mean. And to be very clear, we have equality for A equals B. Great, so there is the two-dimensional arithmetic geometric mean inequality with two letters at the beginning of the alphabet. Now, let's go to a sum of not just two terms, let's go up. In fact, let's go to a sum of four terms. Four terms. And the reason I like four, because I can think of a sum of four distinct numbers as a sum of two terms and a sum of two terms. Right, so by the two-dimensional case, this is greater than or equal to twice the geometric mean of A and B, plus twice the geometric mean of C and D. And to be very clear, to get equality for this part, I would need symmetry. I need A equals B. To get equality for this part, I'll need C equals D. And to get equality for both parts together, I'll need both to happen at the same time, both happen together. All right, great. But now look what I've got. I've got the sum of two distinct terms. By the two-dimensional case, I know this is greater than or equal to twice the geometric mean of these two terms. This thing, twice square root of AB, times twice the square root of CD, square root of all that. Oh, and just to be very clear, for equality, I get equality if my two unknowns have the same value. So I need 2 root AB to equal 2 root CD, divide by 2, take squares. I guess I'll need AB to equal CD to get equality from this line to the next. All right, great. Oh, but look at this. This is nasty. I've got 2 square root of A, square root of B, 2 square root of C, square root of D, all under a square root sign. So I'll get 4 under a square root sign. That's another 2. This actually is 4. Then I'll get the square root of A and square root of B times square root of C times square root of C. I'm doing fourth roots. The square root of fourth root of A, fourth root of B, fourth root of C, fourth root of D, all multiplied together. That tells me that A plus B plus C plus D is greater than or equal to 4 root A, B, C, D, fourth root A, B, C, D. That's called the geometric mean of the four numbers A, B, C, and D. And if I divide by 4, I have the arithmetic mean of the four numbers A, B, C, and D. Whoa! So there is a four-dimensional version of the arithmetic geometric mean inequality. And to be very clear, when we have equality, well, I need this to work to give that equality. I'll also need that to work to give this equality. So I need A to equal B, C to equal D. I'll need AB, but that would be A squared, to equal C times D, but that would be C squared. So I need A squared to equal C squared. Everything's positive numbers, so that means A equals C. A equals B, A equals C, and C equals D. We have equality only if A equals B equals C equals D. We have full symmetry going on right there. So there it is, the four-dimensional arithmetic geometric mean inequality with equality if we have full symmetry going on. Fabulous. Well, that was neat. But if you look at this, it's kind of odd that we've got the two-dimensional version, we've got the four-dimensional version, and we skipped over the three-dimensional version. Can we get this three-dimensional version? Can we say something about the sum of just 3 distinct numbers? Yes, we can, but we have to be a little bit sneaky for this one. So let's try this. All right, clean the board. So I'll go back to thinking about arithmetic means. So here's what I'm going to do. I'm going to do a sum of 3 terms, and I'll let capital A be their arithmetic mean. There it is, the sum of the 3 terms divided by 3. Because what I want to do now is actually do the four-dimensional version using this. How? I'll do my sum of the 3 numbers, plus I'll add a 4th number to this, that arithmetic mean. And think about what this is. A plus B plus C, that's actually 3 A's right there. Plus another A means this is actually 4 A's. This is really 4 A's. We just did the four-dimensional version of the arithmetic geometric mean inequality. We know that's greater than or equal to 4 times the 4th root of A, B, C, A. Whoa! So I've just got that 4A is greater than or equal to 4th root of A, B, C, A. Divide both sides by 4. A is greater than or equal to the 4th root of A, B, C, A. Let's take the 4th powers of everything. a to the fourth is greater than or equal to abc times a. Divide everything by a cubed is greater than the abc, that product. Therefore, the arithmetic mean of a, b, and c is greater than or equal to the cube root of a, b, c, the geometric mean of a, b, and c. There it is. I've now got the three-dimensional version of the arithmetic geometric mean inequality. And to be very clear, to make sure where we've got equality, to get equality here, I need all four of these numbers to be the same. So we need a to equal b to equal c to equal big A. But if a, b, and c are all the same number, then this big A will actually be the same as those numbers as well. That's kind of redundant. So we have equality for a equals b equals c. Again, full symmetry. So there it is. I have now the arithmetic geometric mean inequality for dimensions 2, 3, and 4, and we can keep on going. Earlier, we looked at the squares of the same perimeter and the same area as a given rectangle and found a geometric interpretation of the arithmetic mean and the geometric mean of the sides of that rectangle. And we can do the same thing in 3 dimensions. Here's a rectangular box. I've made it like a wire frame. We've got all these bits of wire making this great big box with dimensions A, B, and C. And of course I could ask, okay, instead of doing squares associated with rectangles, I can now do cubes associated with this. Let's go for the same. Okay, what's equivalent to perimeter? Perimeter would be all the edge lengths of a rectangle, so here I'm guessing doing all the edge lengths, all the length of wire that made this shape. So let's go for the same edge length. So I'm going to look for now for a cube with the same total edge length. So there's a cube with the same total edge length. I'll call it W, W, and W. So I want all those sections of wire here. There'll be 12 W's, to add up the same amount of wire here, which is 4 A's and 4 B's. You don't see the ones hidden behind the picture, and the 4 C's. Bingo. If I want the same edge length, if I want the edge lengths to match, I need this equation to be true. Divide by 12, I need W to be A plus B plus C over 3. That is for a cube to have the same edge length as this box here. I need that cube to have the side length, the arithmetic mean of the original side lengths of the box. Whoa! Okay, so then it seems natural, maybe I'll go with volume next. We did area before, in 3 dimensions, most people think volume. So let's go for the same volume. Let's get a cube of the same volume. Don't yet know what it is, W for don't know what it is, but the same volume, there it goes, would have to have what property? Well, the volume of this cube, which would be W times W times W, W cubed, would have to be the volume of this box, A times B times C, A times B times C. So W would have to be the cube root of A, B, C, the geometric mean. So there is the geometric meaning of the geometric mean in 3 dimensions. It will be the side length of the cube with the same volume as a given box. Beautiful, beautiful, beautiful. And we just proved in 3 dimensions arithmetic mean is always greater than or equal to the geometric mean. So this box here, despite my picture, is always guaranteed to be bigger than that cube there. Those cubes are bigger than those cubes. Wow. Okay, time for some fun with all this. Here's a question. 3 positive numbers sum to 1. Before I read any more, I bet the answer is going to be the symmetrical case. 1/3, 1/3, 1/3. They add to 1. Yeah, what's the question? What is the largest possible value of their product? Okay, we're maximizing something. I bet it really is the symmetrical solution. But let me go through the work. All right, so we've got 3 numbers. I'll just call them A, B, and C. So we have that A plus B plus C equals 1. A sum of 3 things makes me think of the 3-dimensional version of the arithmetic geometric mean inequality. So let me do that. But let me do it this way. Let me write 1 equals A plus B plus C, which according to the inequality is 3 times their geometric mean. Great, greater than or equal to 3 times the geometric mean. All right, so yes, I want to maximize the product. There's the product right there. So let me isolate that. That tells me the cube root of A, B, C is less than or equal to 1/3. I did that correctly, yes. That tells you the product is always less than or equal to 1/3 cubed, 1/27. So I know from the arithmetic geometric mean inequality, this product is always bounded by the value 127. That's the biggest I can hope it can be. In fact, I know it can be that if I have equality here. We get this when I have equality, when I have symmetry, when A equals B equals C, three numbers the same, adding to 1, that is A is a third, B is a third, C is a third, in which case the biggest product is indeed 1/27th. A times B times C, a third times third times third is 1/27th. There it is from the arithmetic geometric mean inequality. All right, let's do another example. This is fun. Okay, this question. Two positive numbers A and B sum to 12. So A plus B equals 12. Great. What's the largest possible value of A squared B? Okay, that looks nice and symmetrical. That looks unsymmetrical. Okay, I'm a little bit nervous right now. Okay, but it does seem irresistible. I've got a sum of two things. So I've got that 12 is A plus B. So by the two-dimensional version of the arithmetic geometric mean inequality, I know this is greater than or equal to twice the sum of the same thing, namely the geometric mean of those two numbers. That's why I'm nervous, because if I do that, I get A times B. I need A squared times B. I need another A in there somehow, which means I need another A in there somehow. How am I going to do that? Because that's not helping that two-dimensional version. Actually, there is a way to get another A in this sum. What if I split that A into two parts? What if I think this 12 is really half of A plus half of A plus B? And do the three-dimensional version of the arithmetic geometric mean inequality on that. Because that would be greater than or equal to 3 times that geometric mean. A over 2 times A over 2 times B. Alright, so 12 is bigger or equal to that. Divide both sides by 3. I get that 4 is greater than or equal to the cube root of, there it is, A squared B over 4. Beautiful, beautiful, grand. Let me cube both sides. Oh golly gee, cube both sides. So 4 cubed, 16, 64. So bad board technique, sorry, 64 is greater than or equal to the cube both sides. A squared B over 4, in which case A squared over B 4 is always less than or equal to 4 times 64, 128, 256. That is always true. Can we actually get this product to be all the way up to 256? Yes, we need equality, 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 equality. We need equality when we've got symmetry. This happens, I don't know if I'm still on the board, this happens when my three unknowns are equal. When A over 2 equals A over 2, guaranteed, equals B. All right, I need A over 2 to B to be the same thing. So I need this to be, okay, this and this all equal. Add up to 12, that better be 4, that better be 4, that better be 4. That tells me I need B to be 4, A to be 8. And let me check. If A is 8, that gives me 64. B is 4, that gives me 4 times 64. I feel like I did that somewhere, 256. Yes, yes, yes. I should write up my final answer neatly, but there it is. The largest possible product is going to be 256, and we actually get it with A equals 8, and B equals 4. Yes, good. There, cool. Let's do another one. All right, let's end today with another classic problem that appears in absolutely every calculus textbook. This one. Of all the cylindrical tin cans of volume 1 litre, so a cylindrical tin can of a particular volume, 1 litre, which uses the least amount of sheet metal to construct? All right, so I'm going to use some metal to make this tin can. I need some metal to make the base, that circular base. I need some metal to make that circular top. I need some metal to make that the sides of the tin can. I want the least amount of metal. That is, I want the tin can of volume 1 litre with the least surface area. That's our challenge. Find of all the tin cans of the volume 1 litre, which has the least surface area. All right, so let's get some variables in this. Let's seems natural to call the radius of the circle r, so I'll do that r. I'll call the height of the tin can h. And what are we given? We're given the volume. The volume is 1 litre, 1 unit. So the volume is given by area base, pi r squared times the height, and we're told that's 1 unit, 1 litre. We'll want to play with the surface area. So what's the surface area? All right, so to make this tin can, I need a circle of metal for the base. That's a pi r squared worth of area. Plus I need another circle of metal at the top, another pi r squared of metal. And for the sides, imagine you cut this can, cut the sides, unroll it. So it's really a rectangle that curled up. The length of the rectangle is actually the circumference of the circle. So this rectangle unrolls, there's the circumference of the circle, and the height of the rectangle is the height of the can. So the surface area of the size is 2 pi r, circumference of the circle, times height, h, plus 2 pi r h. So what I've really got here is 2 pi r squareds. The surface area is really 2 pi r squareds plus 2 pi r h. Okay, give myself a bit more room. I feel like I'm going to need lots of room for this one. But that's our job. We're given that pi r squared h is 1, and our job is to play with this. In fact, our job is to minimize that particular formula right there. All right, okay. So I will follow my instincts. I'm seeing a sum of two terms. I'm seeing one term being 2 pi r squared, another term being 2 pi rh. I know that by the arithmetic geometric mean inequality, this sum 2 pi r squared plus 2 pi rh is greater than or equal to twice the sum of the same thing, twice the same thing, the geometric mean. Okay, so that'll be the square root of 2 times 2, pi times pi, r squared times rh. So that's 4 pi squared r cubed h. 4 pi squared r cubed h. Okay, I'm nervous right now because you saw me like pause right there. R cubed h. I've got information about r squared h. There seems to be a mismatch here. There's a mismatch there. I don't think this is going to be helpful. So maybe I need to do the same sort of trick I did before. Split up one of these terms to get an r squared h to appear instead. All right, I'm going to try that. So instead of knowing that, I'm going to say I know something else. Let's try splitting up, say, the first term. Let's do the same trick we did before. Split this up into two parts. So instead of 2 pi r squared, I'll think of this as pi r squared plus pi r squared plus 2 pi rh. In fact, that's the first formula I wrote down for surface area. I know by the arithmetic geometric mean inequality for 3 dimensions, this is three times their cube root, their geometric mean. Okay, let me not do that. That's getting messy. It's going to be something to the 1/3 power. So it's going to be, what to the 1/3 power? This product. So I'll get pi times a 2 pi. So I'll get some numbers. Then I'll get an r squared times an r squared times an r h. R to the 5th h. I'll get some numbers times r to the 5th times h. No, it doesn't seem to connect. I don't see a connection between that and that. I'm stuck again. All right, well, rather than split this into 2 parts, I'm just now groping for ideas. Let's try splitting that one into 2 parts. All right, instead of knowing this, I'm now going to know some third thing. My third thing to know is that, I'll keep this first one the same, 2 pi r squared, plus split this into 2 parts, pi rh plus pi rh. By the 3-dimensional version of the inequality, this is 3 times the geometric mean of that, the cube root of something, the cube root of the product of these numbers. I'll get a whole bunch of 2's and pi's. I'll get some numbers. I'll get an r squared times r times r. I'll get an r to the 4th and an h times an h squared. Do I like that? Do I like that? I do. R to the 4th h squared is basically connected to r squared h. In fact, I can see right here, okay, this bad board technique, this tells me that r squared h is 1 over pi. Therefore, if I square both sides, I know that r4 to the h squared equals 1 over pi squared. So I know from my given, this is just some numbers times 1 over pi squared is just another number. 3 times the number, 1 cube root of. Whoa! So my surface area is always greater than or equal to some number. It's always greater than or equal to some number. Don't bother working out what the number is. In fact, to get the minimal surface area, I'm going to need equality here. To get the minimal surface area, I need symmetry. I need this to equal that. Beautiful. So that even bothered working out the numbers. So we're going to write this. Minimum occurs, where am I going to write this? Minimum occurs for 2 pi r squared to equal pi rh to equal pi rh. All right, the last part's a bit redundant. So I need 2 pi r squared to equal pi rh. Let's divide both sides by pi, both sides by r. So I get that 2r equals h. I know the minimum occurs when the height of the can is twice the radius. Most people call that diameter. Whoa, that is exciting to me because that brings me full circle for this video series. So look at this. If this is h and this is the diameter, 2r's, there's 2r's, there's the diameter. We're saying to get a can of minimal surface area, please make the height of the can the same as the diameter of the can. That is, if you look side on to the can, so here's this can sitting on the shelf, and you see it side on, what are you seeing? If it's the can that uses the least amount of surface area, is the most efficient can to make, you're looking at squares again. The symmetrical solution is back to being a square solution. Whoa, whoa, and there it is from the arithmetic geometric mean inequality for 3 dimensions. Great stuff.